All right. So far we talk about cryptographic properties of hash functions and how they can be constructed. We mentioned Merkle-Damgard construction and sponge function constructions. Now it's the time to see dedicated designs, see which hash functions used in their history and which ones are broken and which ones are secure. So it's a good idea to start with Md4. It was developed by Ronald Rivest in 1990. It has a block size of 512 bits. Message digest length, in other words, the hash size is 128 bits. It is like a block cipher construction in this case, so it has rounds, and the number of rounds are 48, and the type is Merkle-Damgard. So remember the Merkle-Damgard construction picture. Here the compression function f now is replaced with Md4. So one round of Md4 is given in this picture. So it's a very simple design. We have 4 words, A, B, C, D. So initially you put your IV here, which is fixed in the standards. Then you perform some basic arithmetic operations like modular addition on 32 bits, like here. There's a rotation here. And the Fi's functions are here, uses logical operations like AND, or not. So it's a very simple design. So this is just a one round of it. So you replace this, you repeat this picture 48 times, and at the end you will have final A, B, C, D values. Most probably depends on the standard, but you add these values to the initial IV and produce the 128-bit hash value. So you might think that where I put the message blocks are fed from here at each run. So this 48 runs is just for one block of message. If you have multiple blocks due to Merkle-Damgard construction, you repeat this process for every message block. And in this picture, the KIs are just round constants. So you feed the message 32 bits at a time from here. So the Md4 has no collision resistance because people come up with attacks, and generating a collision takes a few microseconds. So on any laptop, you can generate thousands of collisions in seconds. The premise resistance, there is an attack which requires 2 to the 95 operations. So recall that since the message digest size is 128 bit, a brute force attack would require 2 to the 128 operations, but this number is reduced to 2 to the 95. And this was an IETF standard hash function defined in this RFC. And it was retired in 2011, which is very late date, but still it is now replaced with this RFC. But the thing is that it influenced later designs, Md5, SHA1, or RIPE MD. So let's move on to Md5 and see the difference between Md4 and Md5. So this was just developed by Ronald Rivest 1 year later in 1991 to replace Md4. Block size is the same. Message digest length is the same. Number of runs is now increased from 48 to 64, so that Ronald Rivest thought that this would make the hash function more secure. There's still a Merkle-Damgard construction. So you can see that the picture is almost the same. The only difference is that there is one more modular addition here. Okay, that's all. So as you can see, there is a modular addition here and the number of rounds changed. These Fi functions, I think, are the same, but I haven't mentioned them in Md4, so let's see it Md5. As you can see, the F function is defined in 4 different ways. Since this is a 64 round, in first 16 rounds, we use this F here. In the following 16 rounds, instead of F, you use G. So in the next 16, H, and then I. So as you can see, the operations are AND, or NOT, or XOR operations, which are basic logical operations. So you can imagine that this is a really fast hash function. The problem is that generating a collision requires 2 to the 18 operations. Recall that due to the birthday paradox, a brute force attack should require 2 to the 64. So this attack is way faster than a brute force attack, and it takes less than a second on a regular computer. So it has no security at all. Preimage resistance is this. And important thing is that in 2004, it was shown how to create a pair of files that share the same MD5 checksum. For this reason, MD5 cannot be used in forensics. But as far as I know, many forensic software in Turkey still allows to take MD5 hashes of hard drives, which shouldn't have any value in a court. In 2005, Lansra, Wang, and Weger demonstrated construction of two X509 certificates with different public keys and the same MD5 hash value. So you can forge certificates. And in 2008, it is shown how to fake SSL certificate validity, so certificate authorities should stop using MD5. And finally, in 2012, we observed that the authors of Flame malware used an MD5 collision to forge a Windows code signing certificate. So as you can see, a hash function that is broken years ago is still used by people. As you can see in Windows, they were still using MD5 in some instances. And as far as I know, there's still usage of MD5, even in maybe in Windows 10. I talked to a lot of people in Turkey, and I realized that they still think that MD5 is something secure. This is due to the documentation on the internet, I guess, because people who don't know cryptography just Google it from the internet and realize that people are still talking about MD5. For this reason, they keep using MD5. They store their passwords by taking the hash of them using MD5 and so on, but you cannot use MD5 at all. Here's an collision example. As you can see, there are two different messages, X1 and X2. These are 512 with two messages. Two of them are different. Differences are shown in red. So in this case, the hexadecimal value is 7, and here it is F. So first bit is flipped. Here the leftmost bit is 0, and in this one it is 1. So you just flip a few bits, you obtain a different message. Take the MD5 hash of two different messages, and you will obtain the same hash value. As you can see, since we are giving a few differences here, this is actually referred to as a differential attack. Now we can move on to SHA1. MD5 is broken, MD4 is broken, so we moved on to SHA1 actually in history. So this time it was developed by NSA, so it wasn't developed by academicians. It was first published in 1993, but then they made a small modification. They added a single bitwise rotation in 1995. So I think this rotation wasn't there in SHA0, but they realized that this would make the hash function weak, so they added this rotation. And so the added version is referred to as SHA1, and the previous one is referred to as SHA0. As you can see, the picture still looks like MD5. Only difference is that now the message digest length is increased. So recall that in the previous pictures we had A, B, C, D, which were 128-bit. Now we added one more 32-bit value to make it 160. This is actually due to make birthday attacks harder, because when this is 128, finding a collision using a brute force attack requires 2 to the 64 operations, and 2 to the 64 is not that hard with modern GPUs, CPUs, and FPGAs. If you have dedicated software hardware, ASICs, like people have for Bitcoin mining, you can easily perform 2 to the 64 in a very short time. So this is why they increase it to make the security 80-bit due to the birthday paradox. Now the attack requires 2 to the 80 operations. And they also increase the number of runs from, in MD5, this was 64, now it is 80. So picture is almost the same, as you can see. Now you're feeding the message from here. I provided some test vectors from, I think this was from NIST document. So assume that you are taking the hash of a simple message ABC, which is a very small message. So when you write it in the 512-bit block, as you can see, ABC if you look at the ASCII table, turns into 61, 62, and 63. Now the message ends here, so you have to apply padding. You put a single bit of 1, then fill the rest with zeros. Okay, and at the final part, you write the length of your message. In this case, it is 24 bits, and 24 in hexadecimal turns into this. So you write the length in terms of bits, but maybe, if I'm not mistaken, in current standards like SHA3, you write the byte value here, not the bits. You have to check. I'm not very certain about it. So IVs are fixed. You start with the IVs. And you start with the operations, and here are the ABCD values after the application of each round. So at the end, we will add these initial values to the final value. So if you perform 80 rounds of SHA1 operation, this is the final ABCD values. So you write them here, and the initial values here. You add them. This is not an XOR, by the way. It is really a modular addition. It's a 2 to the 32 modulo addition operation, and these are your hash values. So this is how a hash function works. So what about the security of SHA1? The collision resistance should be 2 to the 80 due to birthday paradox, but Wang provided a theoretical attack, a differential attack, where they stated that there's an attack that requires 2 to the 63 SHA1 operations. So at that time, nobody had that computational power. Actually, nobody had that memory to store all of those hash values. So this attack stayed for a very long time as a theoretical attack, but people always thought that when we have the enough computational power, we can perform this attack in practice. But as you can see, SHA0, which was weaker, you can find a collision for SHA0 with 2 to the 33 operations. So you can easily break SHA0, but SHA1 is not that easy to break. And due to this attack, actually, browsers of Microsoft, Google and Mozilla stopped accepting SHA1 SSL certificates by 2017. If you remember that time, after 1st of January, a lot of websites, the browser gave you a red error saying that this might not be secure to visit this website and so on. This was due to the fact that they were using SHA1 SSL certificates. And in a few weeks, all of these problems are solved. They moved on to SHA2. And actually, this was a right call, because although the attack was theoretical, we knew that it was going to be practical in the future. And we, by the way, for this reason, NIST decided to have a SHA3 competition, which we will talk about in a minute. So during these times, actually a collision was found for SHA1, but this was a free start collision. As you can see, here there are two messages, M1 and M2, which are different, but they are the hash values are calculated with different IVs. So some software allows you to choose IV, for instance, on OpenSSL and so on. You are allowed to choose the IV, but in standards, for instance, if you look at NIST's documentation about SHA1, there they state an IV, and that IV is used by everyone. People don't change it. So this is why we call it a free start collision. So it is not a real collision, but the aim was by the authors to show that they can find a free start collision by performing 2 to the 57 SHA1 operations by using 64 GPUs. And they are saying that if we have more GPUs or faster GPUs, we can also find a collision for the real SHA1. So this was a very important, and they were right actually. 2 years later, now those authors combined their forces with Google, because Google had a lot of GPUs. So they modified the attack, and now they found a collision for SHA1. In this case, you can see that the message is now no longer a 1 block, but 2 block messages. But here the IVs are, the hash values are the same, and they start with the same IV. So this is a real SHA1 collision, so the predictions were correct. and SHA1 was broken. So you might think that this is just a collision attack and it's hard to perform. So I can still use SHA1 for different purposes, but once it is broken, the similar case what happened for Md5 can happen here. A flame malware variant can be, done by using SHA1. For this reason, there's no point of insisting on using SHA1. Okay, for us it is broken, so just move on to SHA2. And there are newer papers where you can provide SHA1 collisions with chosen prefix. So SHA2, so until this part, we talk about all of the broken hash functions. Now there's an example where a hash function is not broken yet. This is again developed by NSA and first published in 2001. This time it allows two different block sizes, 512 and 1024. Message digest length is now, you have four choices, 224, 256, which is actually the most used SHA2 version. So this is referred to as SHA256. But we have also larger possibilities. Number of runs also depends on the message digest length you choose. It is again a Merkle-Damgard construction. As you can see, now we have more words here because we increase the message digest length. Now we start from A to H. Again, all of them are 32-bit values. The picture is almost the same. Again, we have addition of words from here. We have round constant here, but we have different functions like majority function, sigma function, and so on. But the definitions are again very similar to Md4 or Md5. Here they are defined like this. So majority function is this, sigma 0 is this one, and sigma 1 is this one, just rotation and XOR. So it is the number of runs are again large, so and there are many operations. So far nobody came up with a collision attack, but as far as I know, the best pseudo collision attack against this hash function can find collisions when you reduce the number of runs to 46. So the full SHA2 is secure. And there are some pre-image attacks. An attack in 2011 can find pre-images for the 57 runs out of 80 runs of SHA512 and 52 out of 64 runs for SHA256. So as you can see, so far academicians couldn't come up with an attack to break SHA2. So we assume that SHA2 is secure and we use it almost everywhere. And you might think that then why do we have SHA3? We realize that all of the hash functions are broken until SHA2. And SHA2, the design of SHA2 is very similar to previous ones, as you can see from the picture. So NIST realized that if somebody comes up with an attack to break SHA2, then we don't have a plan B. We don't have another secure hash function that we can use. So NIST initiated a competition. Yes, starting from 2007, which ended in 2012. And it received 64 submissions, and 4 of them had contained Turkish designers. And unlike the previous competitions held by NIST, like AES competition, Advanced Encryption competition, NIST allowed designers to tweak their algorithms after round 2. So if you pass from round 1 to round 2, you can make very small modifications to your algorithms. This was somewhat important for the competition. So you can visit this webpage, SHA3 to look all of these submissions and their security, which kind of attacks people found and so on. But the winner was Ketchak, which is now referred to as SHA3, and it was designed by Guido Bertoni, John Damon, Michel Peters, and Gilles Van Acht. Now, as you can see, the block size is really huge. This is due to the fact that now it is a sponge function, so it has a huge internal state, and the rate and capacity values are large. Message digest length is the same as SHA2 because we want to replace SHA2 if we want. So this is why these numbers were fixed by NIST when the competition started. It has a number of rounds of 64 or 80, again, depending on this message digest length. But now it is no longer a Merkle-Damgard construction. It is a sponge construction. Remember the picture I showed you about sponge functions. You can, here, they're actually performing a sponge operation here. And this is why SHA3 is very different than the previous hash functions. It is no longer a Merkle-Damgard construction. So today, as far as we know, SHA2 and SHA3 are secure, so you can prefer whichever you want. But in some platforms, one of them might be faster than the other. So you might choose one of them against the other one. But these are the only two hash functions actually you are allowed to use. Anything other than that, Md5, SHA1, then you lose security.